The project that we did is the loop antenna. The loop antenna should usually be the circular loop. To simplify the problem, we choose to be the rectangular loop. Therefore, in the MATLAB, we choose to have the rectangular shape instead of the circular shape. In the MATLAB code, we first set up the simulation. We've set up the physical constants like C naught and mu, and the unit is all in millimeters. That's why we have the unit is 10 to the negative 3. For the loop coil parameters, we set up the length, the width, the strip width, such as 80, 60, and 5 for the metal strip. The strip has cells number of 3, and the air gap will take 1/3 of the width as the air. The position for the x is negative 130 for the loop, and then we have the lumped gap value as 1.4 10 to negative 12. The feeding port resistance is 10, and then we will use this parameter later. The box has high resolution meshes. The mesh box is starting at negative 120, negative 80, negative 120, and the stopping point is positive 180 and 120. It is the same as the body box we created later. The mesh box has resolution of 2, and this parameter we also will use it later. We then create some mesh parameters, such as the air box. The air box has edge of 150 millimeters. It is the size of the box that contains the loop. The loop we created is really small. It is 80 times 60, but the box is 150. That's the reason why we have a really small loop in this big air box showing the picture above. Then we set up the FDTD parameter structures and the excitation functions. For the initializing, we have the int FDTD function taking the parameters and save it back into the FDTD variable. For the defined Gaussian pulse excitation signal, we have the center frequency and 20 dB corner frequencies. This will take into the function set Gauss exact and take FDTD F0, FC as input, and then save it, overwrite the FDTD variable again. To set up the boundary conditions, we set it all to MER. It has 6 boundary conditions, and we created A brackets and save it back into the BC. Taking this into the set boundary condition function, we will override the FDTD parameter again. After this process, the FDTD structure is done. Then we create the CSX structure. To set up the CSX CAD geometry, we need to using the function int CSX, just like the function int FDTD in the previous step. We create the loop, set up all properties needed. CSX, we then create a metal, and for taking loop as the parameter, therefore our loop is made up with metal. And then we add a lumped element, and we create another lumped element taking 1 and 2 as difference. In the following process, we have the loop antenna structure in the YZ direction only in the air box. Therefore, from line 47 to line 79, we create the strips to contribute this whole big piece of the loop antenna. Line 47 to line 62 is the strips creating in the Y direction. From line 64 to line 79, it is the strips that creating in the Z direction. To start this, we have the starting point and stopping point taking the loop parameters such as the X direction, the width, the length of the structure, and using the add box function taking those starting point and stopping point for the inputs, we save it in the CSX structure. Therefore, one piece of the loop antenna is created. Repeating the previous process, we have the Y direction strips created. It has 4 small elements. As I mentioned, the line 64 to line 79 basically repeat the same process as in the y direction. Therefore, we have also the starting point and stopping point, and they will be the parameters taken by the addBox function and save it back into the CSX structure. Repeating this process for 4 times, we finally finish the z direction strips. Therefore, this whole big piece of the loop antenna is finally finished. Although the antenna structure has been finished, we still need to add some lumped capacities and lumped port as excitation points. We also repeat the same process. We have the starting point and stopping point using addBox function for the creating structure into the CSX parameter. Repeating this process, and then we finish this process. After this, we create a lumped port as excitation points, taking loop parameters such as the air gap, position x, and strip width. We finally create the excitation points. Using a lumped port function, we excitation this signal in the y direction only, because it is 0, 1, 0. The x and z direction is all zeros. Therefore, this signal will only show up in the y direction. Set it true so that we can see the result, and save it back into the CSX port matrix. To finalize the mesh, we create the loop mesh using detect edges function, taking CSX structure as parameter, because in the previous step, we created the air box with 150 millimeters on the side, but the loop only have 550 times 80 in the dimension, and therefore we need the detect edges function to perform here, and we override the mesh parameter. To add a dense homogeneous mesh, we create it in the x, y, z direction, and then we add lines in the x direction for the loop and the cell centered around 0. Only in the x direction, we take the mesh box resolution parameter. We set it to 2, and then we are using it here. To smooth the mesh for the loop and body, we using the smooth mesh function and taking the box resolution parameter again and override the mesh parameter. To add a air spacer, we also create it in the x, y, and z direction, and we repeat the same process. Smooth mesh and taking frequency f0 and fc as the parameter and divided by the unit step and divided by 10. As I mentioned before, we create the body box with starting point and stopping point just exactly the same as the mesh box. After that, we override the CSX structure using addDump and addBox function twice. One is in the x, y direction, the other one is in the x, z direction. In order to add 10 lines in all directions to make space for PML or more absorbing, we create the boundary conditions. Add PML is for adding perfect mesh layers. We take mesh as parameter and override it again. To display this, we finally define the FDTD mesh grid structure and using the function define rec grid and override the CSX structure. To prepare the simulation folder, we set up the directory as simpath and taking this as input for file name as the extension for .xml and override the sim CSX. To clear previous directory, it is the command on 141 line. The other one is for creating empty simulation folder. After that, we're gonna write OpenEMS and activate the write OpenEMS function, taking the directory so that we can save the FDTD structure, CSX structure in that directory. Showing the structure and export as VTK data automatically, we use the function CSXGeoPlot to create the geometric plot. And then we finally run the OpenEMS. Therefore, we can see the whole structure using the function run OpenEMS, taking the directory and simulation file CSX as input. From line 157, we are doing the post-processing part. After that, we are going to plot all the variables and all the magnetic fields we are interested. Here we set up the frequency. F0 and Fc refers to the center frequency and corner frequency respectively. F0 minus Fc refers to the mean frequency. F0 plus Fc refers to the maximum frequency we're going to plot. 501 refers to the step size. We maximize the step size to 500, therefore we will get a better result. We set up the port. Then we have Zn and S11. S11 refers to the reflection coefficient S11, and we will plot it in the following code. P_in refers to the antenna feed power. To get the feeding power for frequency F0, we have P0 in. P0 in refers to the feeding power for frequency F0. Therefore, we have F0 as a variable as input. For the plotting reflection coefficient S11, it was starting from 171. We create a figure, and then we plot the frequency in megahertz for the x direction, and in the y label, we have the reflection coefficient in the dB scale. To plot the reflection coefficient, we have the figure 1. The minimum frequency is 0 frequency, and the maximum frequency is 600 megahertz. The graph should be completely flat, but we have some bounce up and down. That's because we have some tiny errors. To get the better result, we should be able to get the completely flat and only have the corner frequency as 300 megahertz. To plot the feed point mittance, we create a figure. We plot the frequency over 10 to the 6. The first one refers to the real part. The second part refers to the imaginary. And we have the plotting function. After that, we have the X label, Y label, and D legend. From now on, we're gonna plot B1 plus and minus on XY plane and XZ plane as well. From the first line, we have the magnetic field and magnetic meshes using the function read HDF5 dump to calculate the BX, BY, B1P, and B1 minus, normalize the input power as we mentioned now. At the following, we have BX and BY calculated just like in the lecture we taught. And we have B1P refers to B1 plus, represent as the imaginary part of the magnetic field is plus. And B1M refers to the magnetic field B1 was deducted from the imaginary part. To create a 2D grid to plot it on, we're using function NDGrid, and following by the B1 plus plot and the B1 minus plot using p-color plot function. As shown in the figure 3, we have the B1 plus field and B1 minus field. In the B1 plus field picture, we have all the meshes showing up. To simplify the problem, we're just gonna see the B1 minus field. The B1 plus field is exactly the same as the B1 minus field. It has tiny differences, but we cannot see it from eyes. In the B1 minus field, we have the loop antenna showing in the Y and Z direction. Therefore, we only have the signals amplified in the X direction. It is a square wave. Therefore, it is only amplified from negative 0.05 to positive 0.05 has the maximum signal. From line 217, we have exactly the same process as before. We just graphed the B1 plus and B1 minus in the XZ plane. We have the magnetic field and the magnetic meshes. BX and BY calculated exactly the same way, and B1 plus and B1 minus exactly the same as before. To create a 2D grid to plot it on, we use the same function NDGrid, and we have dumped two VDK functions to get the directory so that we can see the graph. We have B1 plus plot and B1 minus plot. It repeats the same process as before, therefore we should get some figures later. In the figure 4, we have the V1 plus and V1 minus field showing the XZ direction. We have two boundary conditions at 0.05 approximately and negative 0.05 approximately. It is because we have excitation points and air gaps in the loop antenna. Therefore, we have some boundary conditions and the breaking ups at the 0.05 and negative 0.05 positions. To compare our result, we find a loop antenna paper so that we can compare the results specifically. In this article, the design and implementation of high-frequency RFID loop antenna for metallic environments. In the figure shown above C and D, we have almost the same boundary conditions. Therefore, we are getting almost the same excitation points. Just we divide the graph into three parts. We have the boundary that the signal breaks up at 0.05 and negative 0.05 shown in the figure we run the MATLAB. In the research paper, we have figure B showing the magnetic field of the loop antenna. We didn't do this in the MATLAB, but we can do this in the future improvements. To sum up, our MATLAB code performs perfectly. But in the YZ direction for the research paper, we have in the XZ direction. The boundary conditions apply, therefore we are getting exactly the same result. We just didn't plot from negative 50 to positive 50. We graph it in the different dimensions, but we are getting exactly the same result. Therefore, our MATLAB working well. This is our electrical engineering to FH3 Group B5 MATLAB Open EMS project on loop antennas magnetic fields. Thank you for watching.